derivation of electrostatic potential. Now consider a charge Q at the origin. Test charge Q naught is moved from point A to point B under the influence of charge Q. Force on the test charge. Test charge Q naught is Fc, the force conservative due to electric field, is 1 by 4 pi epsilon naught Q1 Q naught upon R square R cap. Now see the figure. Is, now if you take the figure like this is the point B. This is our axis. This is our y axis. This is our x axis. This is x. This is y, and this is the point B. This is the position vector RB. This is the point A. The position vector is RA, and the charge Q naught. The charge Q is placed somewhere here at the origin. Now there is a path going like this to this point. At this point, the electric force, see, this is the electric force due to the charge Q, that is the force, conservative force, is acting in this direction. Now the R cap, the unit vector R cap, is in this direction. The applied force is in this direction. Force applied is opposite, so the charge does not accelerate. This is a small length dl. This way, this is the dl. This is the small length dl vector, and this is the length vector dr. The angle between them is theta. Wait a minute, let me write it clearly. Somewhere here it is. Let me write this dl here. This angle is theta, and this point is P. Point P. This is point P. The charge Q naught is here. See, let me write it down. Q naught is here in bracket. The test charge Q naught is here. Now you see, this is the point A. This is the vector RA. Now, in order to stop the acceleration, the acceleration of the charge Q naught, to stop the acceleration. Oh, just a minute. Acceleration of the charge Q naught. A force is applied on the opposite direction. Given by, given by direction, which is given by basically F of A. You can see this FA, applied force. This FA is nothing but opposite of FC vector. And this is nothing but minus 1 by 4 pi epsilon naught Q naught R square R cap. That's the only difference. The electric field, let us write down the electric field. The electric field is given by E vector is equal to Fc upon Q naught. And this comes out to be 1 by 4 pi epsilon naught Q upon R square R cap. This scalar part can be written as E R cap. E R cap. Now, the work done by the electric force or the work done by the conservative force, let us write down work done by the electric force, or if I say it is a conservative force, conservative force is nothing but W initial to final conservative force dot dl. Now if you see this initial to final, this is Fc is what is Fc? Q naught E vector. Now from here I can say Fc is nothing but Q naught E vector. And what is E vector? You can see here Q naught E R cap. This is the study. W conservative initial to final is your Fc as Q naught, you write initial to final E R cap dot. Now this DL, before I write this DL, let me make you understand. The curve was something like this, right? The radius vector was something like this from here. From here it was the radius vector. And the tangent to the curve was something like this, the tangent to the curve. This was the DL. This much is length is the DL length. Now if I just see, this is theta, and see, this is dr. So if I drop the, what is the component of dl along dr? What is the component of dl along dr? See, this is, suppose this is the angle theta, and I make a 90 degrees from here, some 90 from here. So the component of this towards this dr is dl cos theta is nothing but dr. This is the point to note. So dr is dl cos theta. This dl cos theta is dr. Now see, yes. Now in this case, this dl can be written as in the direction of r. In the direction of dr, it is in the direction of r actually. dl cos theta. Let me write down dl cos theta. It is in the direction of r cap because now dl cos theta is dr. This r cap. I hoping you are getting this point. This is the direction of the unit vector r, the radial vector. So dl cos theta along this r is dl cos theta r cap. Now, but dl cos theta is what? dr. So WCI initial to final is Q naught. This r dot r is 1. There is nothing to write in this. Initial to final E. Now dl cos theta is nothing but dr, just dr, and this dot product vanishes because r cap dot r cap is nothing but 1. This is the idea. So initial to final you get EDR. This is what I need basically from the scalar part. This is the scalar part of the thing. Now we will write down the vector, the other part. This is the now the work done by the applied force will take into consideration. This was the work done by the conservative now or the electric force. Work done by applied force. The applied force. Now you see one thing in this applied force. You know that F applied is minus F conservative, whereas my F conservative is minus Q naught E vector R cap. So now W applied initial to final, you can write this as your F applied dot DL initial to final. Now this F applied is from here is minus Q naught E vector initial to final R cap DL in the same sense as DL cos theta, the way I explained you, DL cos theta r cap, and this will be r dot r will be minus, r dot r is 1, r dot r is 1, and therefore in dl cos theta, just as I explained you, dl cos theta is dr. So W applied initial to final is minus q naught initial to final E dr. So see the difference. And of course, if you see this this equation, let me mark this equation. This equation, this equation, and this equation are actually opposite to each other, basically always, because of the minus sign. You can see this, and they are always opposite to each other. Now, when you have obtained this expression, now let us understand the thing, the relation that we get from the work energy theorem. See, let me tell you one thing. See, here from here we will see this work energy theorem. So let me write it. You know, work energy theorem is delta K. This is same as WA plus W non-conservative plus W conservative is equal to delta K. Now, work conservative is always minus delta U. The potential energy is always the minus of the potential energy. Now, since work non-conservative is 0 and the change in kinetic energy is 0. Why? Because we are making the let me write down, because the charge is made to move very slowly. The charge test not charge, charge q naught. Let me write that is test charge, because the charge q naught is moved very slowly, very slowly. So there is no acceleration and hence no change in velocity. So slowly it is moved, and hence no change in velocity, and hence no change in velocity, because there is no change in acceleration. Velocity and no change in acceleration, as no change. Let me take some space here. As no change in acceleration. Now since this condition is there, there is no change here. Yes, this condition is there. Therefore, you can see work applied plus work conservative becomes 0. So work conservative is always of minus of work applied. Now you see from here, if you use this terminology, this potential change in potential energy. So if you use, now see, WC is basically, what is WC? WC is minus delta U. And WC is also from here and here. So delta U comes out to be WA. So if I write it in a straight line, del U, change in potential energy, is equal to WA minus WC. And one more thing, this is Q naught times change in potential. V. This is U, this is V. This is the potential, this is, let me write, change in potential energy. Potential energy. This energy is delta U, and change in potential, electric potential or whatever potential, it is always delta V. Keep this thing in mind. This is U and this is delta V. This is delta U, this is delta V. Keep this thing in mind. Now, if I write this whole expression if I try to write the whole expression in one line, you can see this. This is a very, very important thing. Let me mark it. This relation you need to remember. Let's mark it. This is a very, very important relation. Very, very important relation. Always it will hold. This relation will always hold. This thing is very, very important. Now, let us try to understand what is, now we know two things. We know this work done from here. Conservative, we also know work done by applied. And I have just told you right now that this relation always holds. Del V, del U, and this thing. So work applied, you can either use the expression for work applied, or you can use the expression for work conservative. That's your choice. Now, suppose if you use the work applied or the work conservative, the answer remains the same, because delta V, see here, delta V is nothing but work applied by Q naught. This is same as minus work conservative by Q naught, or the electric, or change in potential energy by Q naught. So change in potential using either this formula or this, whatever you want to use, either of these three, you will always get this as minus initial to final EDR, and there is no change in this. Now, since this is the EDR, this is the potential, this is the potential. Now, suppose I want to find what is the change in potential. Now, see, what I'll do is that, what is the expression for E? I know the expression for E. I already know the expression for E. The change in potential is minus 1 by 4 pi epsilon naught. You take Q out, initial to final, 1 upon R square dr. And this integration, earlier videos also I've told you, the integration of R square dr always comes out to be, now by now you all know it, whether you had maths and physics in class 11th and 12th, doesn't matter. Now you know that this comes, I've told you in my earlier videos also in gravitation. It is almost the same way I'm doing it, that the way I did it there. Only there is a change of expression. There it was a plus, here it was a plus there, and here it is a minus. Now if you see this delta V, now will this after this integration will give this me as Q by 4 pi epsilon naught 1 upon R, because the minus sign of this and this, let me write down initial to final. Now there is a minus here. Now these two minuses will give me Q by 4 pi epsilon naught 1 upon R, initial to final. Now let us see what is the thing then. Now after this, delta V comes out to be, wait a minute, yes, delta V is exactly this. So delta V is Q upon 4 pi epsilon naught. You have R final minus 1 upon R initial. And if you want to find the potential energy now if you want to find the potential energy, that is very simple. The minus sign, yes. Now if you want to find the potential energy, you can see that from here, from this relation only you can use it. This relation is sufficient. Just use this relation. Just use this and this concept, this. If you use this and this, you are done with, because you have already found delta V. Now you need to find delta U. That is potential energy. Now you see, now potential energy from that expression only. Delta U is Q naught delta V. So from here you will get Q naught Q, this Q and this Q naught will 4 pi epsilon naught 1 upon, this is R final to 1 upon R initial. This is this relation which you have got. Now supposing I have to bring up, I have to bring a particle from infinity to the position R. Let us now understand this. To bring a particle, object or charge rather, instead of particle, this particle I was using in gravity, mass and all that. Let's use to bring a charge, test charge rather, I should write the charge. Okay, test charge is Q, Q naught from infinity, R equal to infinity to R equal to say some R. That means, that is, R initial is infinity and R final is R. This is there. R final is R. Therefore, and in this case, the initial potential energy is considered, initial potential energy is 0 at R equal to infinity, and U final is U at R equal to, suppose at R equal to R initial, let me say, at R final equal to R. If I put these values, see, delta U is nothing, you can see, U final minus U initial is equal to Q naught by Q 4 pi epsilon naught. You have R final. You have this R final. The finally, sorry, you are yes, 1 upon R minus 1 upon infinity. If you do this, what you will get, 1 upon infinity, you know, is always equal to 0. So, and U initial is 0. So U final is U minus 0 equal to Q naught Q 4 pi epsilon naught 1 upon R minus 0, because this quantity becomes 0. So now your final expression for potential energy is U equal to Q naught Q 4 pi epsilon naught by R. This R has been written here, and this is the potential energy. Suppose you are bringing a negative charge, just replace. This was, we are bringing a test charge. Suppose I am bringing a negative test charge, just put a minus sign. That means if, let me write it there, if a negative charge is brought, then
Then replace q by minus q. That's all. So this expression, especially if you understand this relation very well, I am talking about this relation properly, then you will not go wrong whether it is electrostats or gravitation or anything. This relation is very an important and fundamental relation rather. You should know this relation very well. So now we have been able to discuss what is potential and what is potential energy. This is the potential energy we were talking about. This is the potential energy. Sorry, this is the potential energy and this was the potential. We just talked about the potential. This is the change in potential. And from there, change in potential, we can get the work applied or work done from this relation. Very important relation as I've marked it here. So with this, we are done.